Okay, it's recording. Okay. All right. So let's start then. So, okay. So all right. So we were talking about the heat equation and the divergence of vector fields and the Laplacian. So what we talked about it in R2, but we can do this in higher dimensions, right? So suppose D is an open subset in Rn, and X is a vector field on D. So it's a map from the domain D to Rn. Okay. So you have your domain D. It could look like this. And at each point in the domain, you have a vector x of p. So x is given by an n-tuple of functions, x1 to xn. And we can define the divergence of x if x is C1 by a similar formula to what we had in 2 dimensions. So it's del capital X1 del little x1 plus the sum del capital Xn del little xn. Yeah. And it satisfies the same properties as in 2 dimensions, namely, you can write it as a limit as epsilon tends to 0 of okay, so I'm just going to write this and then maybe we'll see what these terms mean later in the course. So so the volume of the unit ball into epsilon power n. Okay. And then you have an integral over the boundary of so this divergence at a point P is given in a similar way to the divergence in 2 dimensions. So you take a point P, you take a ball of radius epsilon around it, and then you want to measure the flux out of this ball. So you take the unit normal to the boundary of the ball at each point. So that's just the radial vector, the unit radial vector at each point on the boundary. So this is the normal vector, and then you take the inner product of x and this normal vector. So that measures how much is flowing out of the boundary. So, and then you integrate this with respect to what's called surface area measure of this ball of radius epsilon. Okay, so we'll define this measure formally later in the course. If you know what it is, then it's fine. So So surface area measure of the boundary of the point. All right, so so the only undefined term in this integral is the surface area measure. So we'll define this later in the course. Okay. All right. If you know what it is, then it's fine. Okay. And notice, so this surface area measure, when you integrate this, I mean, the total mass of this measure is what's called the volume of the sphere of radius epsilon. That is some constant times epsilon power n minus 1. So again, you would expect this integral to be of order epsilon power n minus 1. But again, there is some cancellation and you get a quantity which is of order epsilon power n. And when you divide by epsilon power n, and there's a constant which is the volume of the unit ball, then this converges to the divergence as epsilon tends to 0. Okay. And you have the same properties in higher dimensions that if I take the change in the volume of a compact set under the flow, then this is the integral of the divergence over that compact set with respect to Lebesgue measure. So this d lambda, this is Lebesgue measure. Okay. So in higher dimensions also, the flow phi t is volume preserving. If and only if the divergence of x is identically 0. Okay. And then if we have a function u on our domain D, which is a C2 function, then you define the Laplacian of u delta u is defined to be the divergence of the gradient vector field of u. And so since the gradient vector field is the vector field with components del u del x1 up to del u del xn, its Laplace, its divergence is del squared u del x1 squared sum up to del squared u del xn squared. Okay.
Excuse me, I have a question.
Yes.
So what was K here? Just some surface?
K is a compact in Rn. K is a compact in the domain D.
Okay.
So it could be a ball. Let's say K could be a ball in the domain. So
okay.
Integrating. Yeah. So.
Okay. Another question. Why do you define? So you're in the limit of for the divergence, you
Yes.
divide by a volume. Why not?
By an area.
Surface area. Yeah.
Yeah. So that's what I was trying to explain last time as well. That the right thing to divide by is a volume, not an area, because actually this integral, like I was saying last time, there's going to be cancellation from antipodal points. Because see, x is C1 in a neighborhood, C1, right? So
yeah,
this distance is epsilon. If I take the antipodal point on the sphere, this distance is also epsilon. So X will change by an amount which is big O of epsilon, right? So
Yeah.
this inner product minus plus this inner product will be of order epsilon, right?
Oh,
Because,
okay.
because the normal vector here and the normal vector here are opposites of each other, right? So
Yes.
this will cancel out. And you'll get something of order epsilon. When you integrate something of order epsilon over the surface of the sphere, that has surface area of order epsilon power n minus 1. You're integrating something of order epsilon. So then you will get something of order epsilon power n.
Yeah. Okay.
Which is of the order of magnitude of the volume of the ball of radius radius epsilon. So that's why you need to divide by. This thing is nothing but the volume of the ball of radius epsilon, right?
Yeah.
This is volume of B epsilon. Is this okay?
Yeah. All right. Thank you.
Yeah. Okay. Okay. So, all right. So, what I didn't say last time is that we have this important theorem called the divergence theorem. So suppose that boundary D is smooth. Okay. So suppose so that means it's a smooth submanifold of Rn of dimension n minus 1. So if you know what that means, fine. If you don't, we'll define it anyway in the course. Okay, what this means. Okay. So then you can define an outward unit normal vector field on the boundary. So this is a map from the boundary to, well, actually it takes values in the unit sphere. It's a unit vector at each point. So it's a map to Sn minus 1. Okay. This is the outward unit normal. So at each point on the boundary, you have an outward unit normal vector n. Okay. Like this. And then what the divergence theorem says, this is Gauss's divergence theorem. It says that the integral of the divergence with respect to Lebesgue measure over the domain D. So suppose D closure is compact. Okay, suppose D closure compact. So D is a bounded domain. Okay, suppose D is a bounded domain with smooth boundary. Then this integral of the divergence over the domain is equal to the integral over the boundary of the domain of X inner product, the outward unit normal, with respect to the surface area measure of the boundary. Okay, so this is again something we will define. Okay. So this is a measure on the boundary. Okay. So intuitively, what this is saying is that, see, the divergence is measuring how much is flowing out at each point, the flux, outward flux at each point. And the divergence theorem, in fact, one can prove it like this, is, this limit here, there's nothing really special about a sphere. When you define the divergence as a limit of integrals over of the outflux over a small sphere, instead of a sphere, you could take a small cube. Okay. And you could do the same integral over the surface of the cube. All right, and then you divide by the volume of the cube, you'll get the same answer. All right, you'll get the same answer. It converges to the divergence. So here what you could do is you sort of, break up your domain into small cubes. You take a grid in Rn, you break up your domain into small cubes like this. So and then how could you prove this divergence theorem? Well, what you notice is that this integral over the boundary of the domain, right? I can write as a sum of integrals over the boundaries of these cubes. Okay, because if I take any cubes which are in the interior of the domain, right? So then what happens is any face of the cube is common to two cubes, and the outward unit normal from one cube will point this way, but from the other cube, the outward unit normal will point in the opposite direction. So when you integrate over this face of the cube, the two contributions from the two adjacent cubes will cancel because the outward unit normal will change signs, right? So the integrals over the faces common to two cubes will cancel. You'll only get an integral over these small cubes, you see? Okay. And so I can write, you'll only get an integral over the boundary. All these faces will also cancel, right? So you'll only get an integral over the boundary. So this you can write as a sum over some set of cubes, say C. So integral over boundary Ci, x n d sigma Ci. Okay, and then by the definition of the divergence, this thing is roughly equal to the volume of Ci into the divergence of x at a point in the at a point pi in the cube Ci. Okay, and then when you pass to a limit, this sum over all the cubes, this will converge to the integral of the divergence over the domain. Okay, so that's roughly the idea of the divergence theorem. Does this make sense? Okay. Yes?
Yes, it makes sense.
It makes sense? Okay. So that's the idea of the divergence theorem. Formally, we'll prove the divergence theorem in a more general setting. Yeah, but for compact Riemannian manifolds with smooth boundary, we'll prove the divergence theorem. But right now, you can just think of it this way, okay? All right. So we have the divergence theorem. So in particular, this leads to the following. So suppose I have my function u, okay, and well, let me just do one formula about the divergence. So if phi is a function, say a C1 function, then what will the divergence of phi times the vector field xb. So this is going to be sum over I del xi of the ith component of phi x, that is just phi times capital Xi. So this is sum over I. So by the Leibniz rule, it will be del phi del xi into capital Xi plus phi del xi del little xi, right? So the first term, you recognize this as this sum as an inner product. So this is the inner product of grad phi with x. And the second term is phi into the divergence of x, right? So this is the formula I wrote at the end of the last class. Okay. Yes.
Yeah.
All right. Is this okay? Yeah.
Yeah.
Okay. So if phi is equal to, so if x is equal to the gradient of u, then we get that the divergence of function phi times grad u is equal to inner product grad phi grad u plus phi, and then you'll get divergence of grad u, that is Laplacian of u, right? So now suppose that phi vanishes on boundary D. Okay. Then by the divergence theorem, if I integrate the integral of this divergence of phi grad u d lambda, this will be the integral over boundary D of inner product of phi grad u with the normal vector, and that is 0, right? Because phi is 0 on the boundary. So this divergence term vanishes. So therefore, that means the sum of these two integrals is 0. So that gives you this integration by parts formula, which I mentioned at the end of last class, that the integral of grad phi grad u d lambda over the domain D is equal to minus the integral of phi Laplacian u d lambda. Okay. So in particular, if I take phi equal to u, then this implies that the integral of u Laplacian u d lambda is equal to minus the integral of norm grad u squared over the domain D. Okay. Which is less than or equal to 0. So this is if u vanishes on the boundary. Okay. So here, if u restricted to boundary D is 0. Is this okay? Yeah.
So the last expression you can also obtain as like this is the divergence of u dot
grad u, right?
I don't understand. What are you saying? Sorry.
So the last expression that we have written, integral over du Laplacian u d lambda equals to negative of that. So if you change this side and bring everything in on one side, then this is just a divergence of u dot grad u, right?
Yeah, that's what I used to get to derive this, right? That's what I
Yeah.
used to derive this, exactly. Yeah.
Yeah.
That's how I derived this, right? So
Uh,
using this formula, right? So I mean, this divergence of phi grad u, this integral becomes 0 if phi vanishes on the boundary. So that means the sum of these two integrals is 0. That means this integral is minus this integral, right? That's how I derived it using the divergence theorem. I derived it using the divergence theorem, exactly. Right, so. Okay. All right. Okay, so I want to talk about the heat equation. So now suppose I have F is a smooth function on D closure. Yeah. And I have a solution to the heat equation. So that will be a function u from the domain D. So let's say D closure across 0 infinity to R. Yeah. A smooth function such that del u del t is equal to Laplacian u, and u of x comma 0 is f of x. Okay. So this is for all x in the domain D. And for all time, I can also fix the boundary condition. So the solution of the heat equation, you have a unique solution once you fix the boundary condition. So suppose on the boundary, I fix it to be f of xi, if xi is in the boundary. Okay. Okay, so I'm not going to go into the existence of this solution. Such a solution exists. Okay. Such a solution exists. What I want to talk about is the fact that I mentioned at the end of last class, that a solution will converge to a harmonic function in the domain D whose boundary value is equal to f. Okay. And so it will be a solution to what's called the Dirichlet problem for the function f on the boundary of D. Okay, so I want to give a little sketch of the proof of this, because the main goal of this course is essentially to prove the same theorem in a nonlinear setup. Okay, for harmonic maps, we will have what's called a nonlinear harmonic map heat flow. That will be a sort of nonlinear heat equation. Okay, but the idea is, under certain hypotheses, we can still prove convergence to, instead of a harmonic function, convergence to a harmonic map. But I want to give you an idea of how the proof goes in the situation of, in the case of functions, okay, which is the simplest case. So here we can actually, it's not too hard to see that a solution converges to a harmonic function. So first of all, two things are very useful. So there's the maximum principle. For the Laplacian. Okay. So this says that if say U from D closure to R, so say U is continuous on the closure of the domain D. D is again a bounded domain. So it's continuous on the compact D closure, and say C2 inside D in the interior. Okay. And if the Laplacian of U is greater than or equal to 0 in D, then the maximum of U is attained on the boundary. So the maximum over the domain D is the same as the maximum over the boundary of D. Okay. So I can give you a sketch of the proof. It turns out, first of all, the Laplacian it can also be obtained as a limit of mean values, a difference of the mean value from the value at the center. So what that means is, again, you take a small sphere of radius epsilon. Okay. And you take the average value of U over the sphere of radius epsilon. Okay. And then, so the average value will be 1 over the volume of the sphere of radius epsilon, SP epsilon, and then you'll have the integral over the sphere of radius epsilon, U d sigma epsilon. This is again surface area measure on the sphere. So this is the average value, right? This minus the value at the center. Okay. If you take this and you divide by epsilon squared, okay, then this will converge to 1 over 2n times the Laplacian, okay, where n is the dimension here, wherein Rn, so limit epsilon tending to 0. Okay. So the Laplacian measures how far U is from satisfying a mean value property on small spheres. Okay. We'll prove this formula later in the course. Okay. In a more general setup for Riemannian manifolds, we'll prove this formula. Okay. So if you have this, then notice that if P is a local maximum of U, then the Laplacian of U is at P is going to be greater than or equal to 0, because the value at P will be greater than equal to the value on a small sphere. Sorry, it'll be less than or equal to 0. What am I saying? Sorry, the Laplacian will be less than or equal to 0. Sorry, at a maximum, it will be less than or equal to 0. right? Because this will be greater than or equal to the average value on the sphere, right? For a small sphere. Is this clear? Yeah, so this limit will be less than or equal to 0. Okay. So to prove the maximum principle, what you can do is you consider a function for an epsilon small, you consider a function u epsilon of x is ux plus epsilon norm x squared. Okay. So then the Laplacian of u epsilon, this is going to be the Laplacian of u plus, so the Laplacian of norm x squared, this is summation xi squared. If I differentiate each xi squared twice, I'll just get 2 with respect to xi. So this will become 2n epsilon, right? Okay. And we're assuming that the Laplacian of u is greater than or equal to 0. So this will be greater than or equal to twice n epsilon, which is strictly positive. Okay, so here I'm taking epsilon strictly positive. All right. So if the Laplacian of u epsilon is strictly positive, then that means by this earlier observation, it cannot have any local maximum in the domain, right? Because at a local maximum, the Laplacian will be less than or equal to 0. But if the Laplacian is everywhere strictly positive, then that implies that, so if I say, so this is if a local max in the domain D, then the Laplacian is less than or equal to 0. So by this observation, the maximum of u epsilon has to be attained on the boundary of D, right? So there exists x epsilon in boundary D such that u epsilon of x epsilon is equal to, oh, sorry, this should be D closure. Yeah. So the max of u epsilon over D closure, right? So now you let epsilon n tend to 0. You take a sequence tending to 0. Then you take the corresponding points x epsilon n. Okay, so these are in the boundary, so they converge to some point x naught in boundary D along a subsequence, because boundary D is compact. And then since the x epsilon n's are the maxima of u epsilons, and the u epsilons converge uniformly to u, that implies that u of x naught is the maximum of u over D closure. Okay, so the maximum is attained on the boundary. Is that clear? Yes?
Why was ux not the maximum?
Because u epsilon converges to u uniformly, right?
Okay, okay. Yeah.
From there, the maxima will converge to a maxima. That's an easy observation, right? So, right. And the maximas of u epsilon, any limit of maxima of u epsilon has to be a maxima of u, right? Is that clear?
Yeah, it's clear.
Okay, that's it. So, okay. Okay, so that's the maximum principle for the Laplacian. Now, there's also a maximum principle for the heat equation or for the heat operator. So let's define the heat operator. This is also very useful, this maximum principle. so L, this is the Laplacian minus del del t. Okay. So this is an operator acting on functions in n+1 variables. Okay. And so now, if I have a domain D, what I can do is I can look at the domain cross time. So I get a sort of cylinder. Uh, this D. Oh,
Your voice is breaking.
sorry, it disconnected. Okay, so okay, let me just share again. Okay. All right. So we have the maximum principle for the Laplacian. Now we have another maximum principle for this heat operator, which is the Laplacian minus del del t. So here we have to define this cylinder domain d sub t, which is d cross 0t. And then so the this vertical part of the boundary, this is boundary d cross 0t. Okay. And then you define what's called the parabolic boundary of this cylinder. This is defined to be d cross 0 union, so that the bottom union the vertical sides, so del d cross 0t. Okay. Okay, so the parabolic boundary will be this part and this vertical part, everything except this top boundary. Okay, this is the parabolic boundary. And then we have this maximum principle for the heat operator. So suppose now U is what's called a C2, 1 function on d cross 0t. So what that means is it is C2 in the space variable and C1 in the time variable. Okay. So suppose we have such a function, and then the parabolic maximum principle, it says if Lu, this heat operator applied to U, is greater than or equal to 0 in this cylinder, then the maximum of U over the cylinder is equal to the maximum of U over the parabolic boundary. Okay. And so the maximum is attained on this parabolic boundary. That's what the maximum principle is saying. Okay. So the proof is very similar to the proof of the maximum principle. So what you do is, again, you take a small perturbation of u. So now you take a perturbation in the time variable. So you say you let un of x comma t, you let this be u of xt minus 1 over n into t. Okay. So then you let xn tn be a point in this cylinder where un attains its maximum. Okay. All right. So now notice this is a maximum in both as a function of both the variables. So in particular, so well, let's see what that means. So the claim is that if xn belongs to the interior of the domain D, then Tn has to be positive. So, sorry, Tn has to be 0. Sorry. Tn has to be 0. Sorry, Tn has to be 0. So the proof is, suppose not, so xn belongs to the interior of the domain D and Tn is positive. Okay, so if Tn belongs to the open interval 0 open T, right, then I can differentiate at Tn I can differentiate with respect to T at Tn, and since this is a maximum as a function of T also, so therefore the first derivative del u n del T at xn Tn, this has to vanish, right? Because this is a maximum with respect to the T variable also. Okay. Yes. Otherwise, if Tn is equal to capital T, then I can take a one-sided derivative, then del un del T at xn comma Tn, this is equal to the limit epsilon tends to 0. So what is the partial derivative? It's going to be un of xn comma capital T minus epsilon minus un of xt, the whole thing divided by minus epsilon, right? And so the top un of xt is greater than or equal to un of xt minus epsilon. It's a maximum. So the top is less than, the numerator is less than or equal to 0. The denominator is negative. And so this will be greater than or equal to 0. Okay. So in either case, del un del T at xn Tn is greater than or equal to 0. So thus, in either case, zero is less than or equal to del un del T of xn tn. Okay. And this is equal to del u xn tn del t minus 1 over n. Okay. Now I can use the hypothesis that the heat operator applied to u is non-negative. So that means that the heat operator, remember, was Laplacian minus del del t. So if this is greater than or equal to 0, that means that del u del t is less than or equal to Laplacian u if Lu is greater than or equal to 0, right? So under this hypothesis, I will get that this del u del t xn tn, this is less than or equal to Laplacian u xn tn minus 1 over n. But the Laplacian of u in the space variable, I mean, un differs from u by a function of time, right? So in the space variable, they differ by a constant. So the Laplacian of u is the same as the Laplacian of un. Okay, so this is Laplacian un xn tn minus 1 over n. And un in the space variable, because xn is in the interior of the domain D, I know that the Laplacian will be less than or equal to 0, right, at a maximum. Okay, so this will be less than or equal to minus 1 over n. But that's a contradiction, right? Okay. Is that clear? So that proves the claim. So therefore, if xn belongs to D, then Tn is equal to 0. Otherwise, xn belongs to boundary D. So this implies that xn Tn belongs to the parabolic boundary, del P of dt, right? Is this clear? Yes? Yeah, the parabolic boundary was, I mean, D cross 0. So that's this case. Otherwise, boundary D cross 0t. So you have to be in one of these two cases. So that means xn Tn belongs to the parabolic boundary. Okay. And this again, as n tends to infinity, along a subsequence, this will converge to some x naught t naught, which is in the parabolic boundary because it's closed. The parabolic boundary is a closed subset of the cylinder, such that, again, because un converge to u uniformly, this means that x naught t naught will be a maximum of u. Is this clear?
Yes.
Okay, so that's the proof of the parabolic maximum principle. Okay,
I
any
have a
questions?
question.
Yes,
So, what is parabolic boundary?
I defined it here.
Oh, maybe I
This
missed
part
it.
of the boundary, this part of the boundary, it's D cross 0 union boundary D cross 0t, right?
Yes.
So that means
Okay.
the whole
Okay,
part
okay.
of the boundary except the top. It's all
Yes.
of the boundary except this top part, right?
Yes.
That's the parabolic. Okay.
Yes.
So this parabolic maximum principle, it is immediately going to tell me that this solution of the heat equation, this is uniformly bounded for all time. Right? Because if I look up to time t, right? If I look at this solution of the heat equation, then what are my boundary values? Over here at time 0, u is equal to f at time 0. And also on this vertical boundary, u is also equal to f here, right? F restricted to boundary d here. So f is a fixed bounded function. So that means that the maximum of u will be attained on this parabolic boundary. So it's going to be just some value of f, which is a fixed function, a bounded function. And also similarly, by considering minus u will also be a solution of the heat equation, right? With boundary values minus f. So the minimum, applying the parabolic maximum principle to minus u, you'll get that the minimum is also attained on the boundary. And so the minimum will also be some value of f. So the maximum and minimum of u will be bounded. And so mod u will be bounded. Okay? For all time. Is that clear? Yes? Okay, so the parabolic maximum principle implies that for the solution of the heat equation, right, the slope of u over d cross 0 infinity of mod u, this will be less than or equal to the sup norm of f on d closure. Is this clear? Yeah. So the solution of the heat equation will be uniformly bounded for all time. All right. Is this okay?
Yeah.
Yeah, fine. All right. Okay. Okay. So now I want to come to the energy, right? So we were talking about the energy of a map last time. So okay, so we saw, so suppose if ut is a one parameter family of functions, a smooth one parameter family of functions, such that, let me assume that ut restricted to boundary d, this is constant in t, okay? So I'm not changing the values on the boundary. Okay. So then that means that if I look at del u, del ut, del t, then this restricted to boundary d, this is equal to 0. Yeah. So if I look at now the energy of ut, this is equal to the integral over d of half norm squared of grad ut d lambda. Then what is ddt? of the energy of ut. So this is going to be, so if I differentiate this, what will this be? This will be half integral over d. This norm squared of the gradient, this is the sum del ut, so I'll just write, yeah, del ut del xi whole squared. Okay, so I'm taking del, by differentiation under the integral sign, I take the derivative inside the integral. So this will be del t of this, right? So when I differentiate, what will I get? I'll get twice del ut del xi into del t of this. So the twice will cancel with the half. So that will give me sum over I del u t del xi into so here this del t of del xi of ut, I can interchange derivatives, right? So then this becomes del xi of del u del t, right? By, since u I'm assuming is smooth in space and time variables, so I can interchange the space and time derivatives, right? So then this becomes the integral of the inner product between grad ut and grad of del ut del t, right? Okay. And now del ut del t, this is a function which vanishes on the boundary. So I can use my integration by parts formula from before. And this is going to be therefore minus the integral over d of del ut del t into Laplacian of ut, right? Okay. Is this clear? Yeah. Yes, is this all right?
Yes.
Okay. So so what this says is that you can view harmonic functions in the following way. That so you say, so given u in C2D, you say that a family ut t in minus epsilon epsilon is a compactly supported variation of u if so u0 equals to u and there exists a compact k in D such that ut is equal to u on d minus k for all t. Okay. So outside a compact, I don't change u. Okay. So this implies that del ut del t is equal to 0 on d minus k. Okay. So then we have the following characterization of harmonic functions. So first of all, Laplacian u equal to 0 in D if and only if. So this I can say that a function is 0 if its integral with respect to all compactly supported functions, smooth compactly supported functions, is 0, right? So for all phi in CC infinity D, the integral of Laplacian u times phi is 0, right? Okay. And this is the same as saying that this you can see as the derivative at time 0 of the energy of a compactly supported variation of u. Right? Is this clear? From this above formula for the variation of the energy, the derivative of the energy, right? So at time 0, we get that ddt at t equal to 0 of energy of ut is minus the integral of Laplacian u into del del t at t equal to 0 of ut d lambda, right? Okay. So if this integral of Laplacian u times phi d lambda is 0 for all phi, then this ddt of the energy is 0 for all compactly supported variations, right? Yeah, because this function del del t of ut at t equal to 0, this is compactly supported in the domain D, right? So this integral will be 0. Whereas conversely, if this derivative of the energy is 0 for all compactly supported variations, then this integral of u times phi Laplacian u times phi will be 0, right? Because given any phi in CC infinity D, you just put u of t equal to u plus t phi, right? So then del del t at t equal to 0 of ut will be equal to phi. And so if this derivative of the energy is 0, then the integral of Laplacian u times phi will be 0. So is this clear?
Yeah.
Yeah, okay. So what does that mean? That means we have another characterization of harmonic functions. So harmonic functions can be thought of as what are called critical points of the energy functional, right? They are critical points of the energy functional. That means, well, I mean, it just means that the derivative of the energy along any compactly supported variation of u is 0. Okay. I mean, formally speaking, later we'll talk about derivatives of functions even in infinite dimensional vector spaces and so on. So one can interpret this statement in a more formal way, where the derivative of the energy becomes a linear map on a space of functions, and the harmonic functions are exactly the functions in the kernel of the derivative of the energy and so on. It's a critical point of the energy function, a point where the derivative vanishes. So, but this is good enough for us right now. Just talking about compactly supported variations of a function. Okay, so without getting into function spaces and so on, and thinking of the energy as a function on some function space, it's simpler to just look at variations of a function and look at the energy along variations of a function. Okay, so harmonic functions you can think of as critical points of the energy functional. Okay, so harmonic functions are critical points of the energy function. So critical point here just means exactly this, that the derivative of the energy along any compactly supported variation is 0. That's all it means. Okay, nothing more. So, okay. All right. So now let's come back to the heat equation. So suppose U of xt is a solution of the heat equation with the given boundary conditions. So fixed boundary conditions. So U of x0 is fx, and U of xi t is f of xi for xi in boundary D. This is for x in D. Okay. Then let me look at the function u sub t of x. This is u of xt. Okay. So this is my one parameter family of functions. Now what I said last time is that the energy of these functions ut will be decreasing in time. So we can see that easily because so ut restricted to boundary D, this is constant, right? Equal to f restricted to boundary D. Okay. So now what is the derivative of the energy? So this, by the formula we derived, this is minus the integral over the domain of Laplacian of ut into del u del t, right? Del ut del t d lambda. Okay. But Laplacian ut, since it's a solution of the heat equation, this is going to be minus integral over t of del ut del t whole squared, right? So this is less than or equal to 0. Okay. So that means the energy is decreasing. All right. So the energy is decreasing in T. Okay. But now we can actually say more. Let's look at the second derivative of the energy. So what will that be? So the derivative of the energy is minus the integral of del ut del t whole squared. So when I differentiate again, I'll get minus 2 integral over d, and then I have to differentiate this. So I'll get, well, del ut del t into del t of del ut del t, but del ut del t I can write as Laplacian ut, right? But now again, I use the observation that we made earlier, that space and time derivatives commute, right? Because
Isn't there an additional minus sign when you're making that substitution?
no, I have this minus here, right? So that will stay a minus here.
Okay.
No, I mean, the heat equation is what? Del ut del t is equal to Laplacian of ut, right?
Oh, okay, then it's fine.
That's the heat equation. Okay, so when I make the substitution, I'll get this. Okay, now I can interchange space and time derivatives, right? So this becomes minus 2 integral over the domain D del ut del t into Laplacian of del ut del t, right? I interchange space and time derivatives. Okay. Yes. And now notice that del ut del t, this is a function which vanishes on the boundary because we're keeping the boundary conditions constant, right? Therefore, I can use the integration by parts formula and say this is minus 2 into this integral will be minus the integral over d of the norm squared of grad of del u del t. Right? This is the formula we derived earlier. Yes? Because the boundary condition is 0 here, so we can apply this formula. Is this clear? Right?
Yeah.
Yeah, we derived this above. Look, we derived this above. So
Yeah, it's clear.
yeah, over here, right at the beginning, right? This u Laplacian u is minus integral of norm grad u squared, right? If u restricted to boundary d is 0, right? So I'm using this formula in place of u, I'm putting del u del t. That is 0 on the boundary. So I can apply this formula, right? Okay. Yes?
Yes.
Okay, so I get a minus and a minus. So this is equal to 2 times the integral over d of norm of grad del ut del t whole squared d lambda. Okay, so this is greater than or equal to 0. So that means the energy function, its second derivative is greater than or equal to 0. So it's a convex function. Okay, so now it's a decreasing convex function, right? So which is greater than or equal to 0 because it's the energy. So it's non-negative, right? So just think of what the graph of a decreasing convex function will look like. So notice that, we know that ddt of E of ut, this is less than or equal to 0. So this is bounded above, and this derivative, first derivative is increasing, right? ddt of energy of ut, sorry, ddt of ut, this is greater than or equal to 0, right? So it's a monotone increasing function which is bounded above by 0. So therefore, ddt of ut, of energy of ut, this converges, this increases to some number alpha less than or equal to 0 as t tends to infinity, right? This converges. Okay. Yes.
Yeah.
Now, that means the slope of the energy function, the slope is converging to some number less than or equal to 0. Now, if alpha is strictly negative, what will happen? If it converges to a strictly negative slope, then that means that the energy function will tend to minus infinity, right? This can't happen because the energy function is greater than or equal to 0. After all, right? It's integral of a norm squared. So alpha cannot be negative, right? That means alpha has to be greater than or equal to 0. So it has to be equal to 0. Is that clear? Yeah, if it had slope alpha, which is negative, then the energy of ut would tend to minus infinity, right? Okay, look, see the derivative of the energy function, this is less than or equal to alpha, right? So that means that if I integrate, I'll get that the energy of ut, this is less than or equal to energy of u naught plus alpha t, right? Yes, for all t. So the right-hand side, this converges to minus infinity if alpha is strictly negative, right? That's a contradiction because the energy is greater than or equal to 0. Right? Yes?
Yeah.
Okay, so therefore, that means that alpha must be equal to 0, right? Okay. So this can't happen. This is a contradiction. So what happens is actually the energy function has to look something like this, right? It's monotone decreasing and bounded below by 0. So it converges to a limit. Okay, so it looks something like this. Okay, this is energy of ut. Okay, this is what the energy function has to look like. It's a monotone decreasing convex function, which converges to a limit. Okay. Is this clear? Now, this alpha 0 means that the derivative of the energy function goes to 0. But what was the derivative of the energy function? That was minus the integral over boundary d of del ut del t whole squared, right? D lambda. Yeah, but this is equal to minus the integral of Laplacian ut whole squared, right? By the heat equation, d lambda. So that means this converges to 0 as t tends to infinity, right? Okay. So the L2 norm of the Laplacian goes to 0, right? Okay. Is this clear? Yes?
Yeah.
Right. So therefore, we get the following. If ut converges to some u infinity in C2 norm, okay, so that means the second derivatives converge uniformly on D closure, right? Then that means that Laplacian ut will converge to Laplacian u infinity uniformly on D closure. And that will imply that this integral will converge to, so the integral of Laplacian u infinity squared d lambda will be equal to the limit t tends to infinity of integral over d Laplacian ut squared d lambda, and that will be equal to 0. And that will imply that the Laplacian of u infinity is 0, right? Okay, so that means that if my solution to the heat equation converges in C2 norm, then any limit is a harmonic function, right? Is it clear?
Yeah.
So the only possible limits of the heat equation have to be harmonic functions. Okay. So in fact, this is true for a subsequence, right? If I take a sequence UTN, which converges to U infinity, then Laplacian of UTN goes to Laplacian U infinity. And so this becomes limit n tending to infinity. Right? And this is 0. Okay. So any limit of a sequence taken along the heat equation, a solution of the heat equation, any limit in C2 norm has to be a harmonic function, right? Okay. Now we can prove that, well, now the point is what happens is actually that this is a classical fact which I will not, I don't want to spend too much time on this. Okay, maybe, all right. So the fact is actually that this is a classical fact that this ut t in 0 infinity this is bounded in what's called C2 alpha of D closure. Okay. So what is this? This is what's called a Holder space of functions. So here I have to define for you what are Holder spaces. So if so you know what the C2 CK spaces are, right? There you take basically the supremum norms of all the partial derivatives of order k, and then you add up those sup norms, right? So here you do that, you take the C2 norm, and then you also add up what are called the Holder semi-norms. So what is the alpha? So if alpha is a number in between 0 and 1, okay, then you can define what's called its Holder semi-norm.
Could you repeat what you said?
Yeah, I'm defining. So a Holder semi-norm of a function phi. Okay, this Holder semi-norm, this is defined to be the sup over x, y in D x not equal to y of mod phi x minus phi y over distance xy to the power alpha. Okay. And then what is the C2 norm of what is the C2 norm of phi? This is defined to be the sup norm, okay, plus sum over I, the sup norms of its derivatives, first derivatives, del phi, del xi, plus the sum over ij, the sup norm of the second derivatives, del squared phi, del xi, del xj. Okay, this is the C2 norm, all right. And what is the C2 alpha norm? So the C2 alpha norm is defined to be the C2 norm of phi plus the sum over ij, the Holder semi-norm of del squared phi, del xi, del xj. Okay. All right. So is the definition clear? Okay.
Yeah,
And yeah, and then C2 alpha declosure. This is a Banach space. This is defined to be the phi in C2 of declosure. So that means partial derivatives of order 2 exist and extend continuously to the boundary. Okay. So phi in C2 declosure such that this C2 alpha norm is finite. Okay. So this is a Banach space with this C2 alpha norm. All right. This is the Holder space. Okay. Similarly, I should just say there's a C alpha norm. So C alpha of declosure is phi in C0 of declosure such that the C alpha norm of phi, this is defined to be the sup norm plus the Holder semi norm of phi. This is finite. Okay. And then there's a fundamental theorem called the Schroeder estimate. So suppose D in Rn is a bounded domain with smooth boundary. And suppose alpha, you fix an alpha between 0 and 1. Okay. So then if U is a continuous function on D closure, which is C2 on D, is such that so one Laplacian of U is equal to F for some F in C alpha D closure, and to U restricted to boundary D is equal to psi restricted to boundary D for some psi in C2 alpha D closure. Okay, then the C2 alpha norm is less than or equal to some constant k times the C alpha norm of F plus the C2 alpha norm of psi. Okay, for some k, which only depends on the domain D and alpha. Okay, this is the Schroeder estimate, the boundary Schroeder estimate. There's another Schroeder estimate called the interior Schroeder estimate. But this is the boundary Schroeder estimate. So is the statement clear? Yes?
Yes, sir.
Okay. So you see, what's interesting here is that the Laplacian is just a particular combination of second derivatives of U, right? Whereas this C2 alpha norm, this involves the sup norms of all the second derivatives of U, right? So we're getting control of all the second derivatives of U just from control on the Laplacian of U, right? That is F. Okay. So for the solution of the heat equation, what that gives you is that so here we had okay, so for the heat equation we had that Laplacian ut is equal to del ut del t, right? And ut restricted to boundary D is equal to some function f restricted to boundary D, right? Where f I can take to be smooth up to the boundary. Okay, so this is contained in C2 alpha of D closure. Okay, so what I'll get is an estimate that C2 alpha norm of ut, this will be less than a constant times the C alpha norm of del ut del t, right? Plus a fixed constant, the C2 alpha norm of F. Right? For UT, a solution of the heat equation. Is this clear? Right? By the Schroeder estimate. To show, so therefore, to show that this is bounded, the C2 alpha norms of UT, I just need to show that these time derivative, the C alpha norms are bounded, right?
Yes.
Okay, and this one can show using the maximum principle. So, well, actually, well, we can at least show that the C0 norms are bounded, and with a bit more work, you can get the alpha norms too. So, I mean, for example, for the C0 norms, if I look at, let me call this, say kappa T, this is half del UT del T whole squared. Okay. Then what is del T of kappa T? This is going to be, so I differentiate, I'll get del UT del T into del T of del T UT. So that will be del T of Laplacian UT, and this will be, again, I interchange space and time derivatives. This will be Laplacian of del UT del T, right? Okay, so this is del T of kappa T. And what is Laplacian of kappa T? Well, there's a formula for the Laplacian of a product, Laplacian of F times G. You can work this out for the Euclidean Laplacian. This is very simple. This is just F Laplacian G plus G Laplacian F plus twice inner product Laplacian F Laplacian G. So if F is equal to G, then this will give me, so there's a half here. So half of this squared. So I'll get basically del UT del T into Laplacian of del UT del T, right? Plus, so this twice and there's a half here. I'll get norm of grad del UT del T whole squared, right? Okay, so this is equal to, this first term is del T of kappa T, right? So this is del T of kappa T plus something positive. So this is greater than or equal to del T of kappa T, right? So that implies that L of kappa T, that is Laplacian minus del T of kappa T, this is greater than or equal to 0, right? So therefore, I can apply the parabolic maximum principle for the heat equation. So that means that kappa T, right? This is, so less than or equal to the SOAP over, so the value at the bound, at the, so the SOAP over 0 less than or equal to S less than or equal to T. Kappa S restricted to boundary D, right? So the max of this and all right, let me just. So this is less than or equal to the max of So I have to take the supremum over the parabolic boundary. So there's one part which is where the domain D cross 0. So that's at time 0, right? So that's the sup over D closure of kappa 0. So that's some fixed constant. And then there's the vertical part of the parabolic boundary. So that will give me a sup over 0 less than or equal to S less than or equal to T. Sup over boundary D of kappa S, right? But on the boundary, kappa S was what? Kappa was half del U del T whole squared, right? On the boundary, U is constant in time, right? So kappa T restricted to the boundary of D is 0, right? So this part which depends on time, this is 0. Okay, so only this part remains. So this is some constant C, okay, independent of time. Is that clear? Yeah.
Yes,
Okay.
sir.
Yes, it's clear.
So what does that mean? That means that this time derivative squared, so that means that the sup norm of del ut del T, this sup norm is less than or equal to C, so this squared is half of this squared is less than or equal to C, right? For all T. Okay. Is that clear? Yeah, and from that you can, well, you have to do a bit more work to bound the alpha Holder norm, the semi-norm, but yeah. But essentially from that and the Schroeder estimate, you'll get a bound on the C2 alpha norms of the UTs, all right? Okay, because you're bounding this becomes bounded by a fixed constant in T, and this is constant. So this becomes bounded for all T. And once you have that bound, then what you get that norm UT C2 alpha. This is less than or equal to some constant C prime for all T. Okay. But once you have this, what does that mean? That means, first of all, the second derivatives are uniformly bounded, right? And also their Holder semi-norms are uniformly bounded. The Holder semi-norms of the second derivatives are uniformly bounded. That means the second derivatives become equicontinuous, right? So that means second derivatives of UT are uniformly bounded and equicontinuous, right? Is that clear? Because they're uniformly alpha Holder, right? Because they're the alpha Holder semi-norms of the second derivatives are bounded, so they become equicontinuous, the second derivatives. Is that clear? Yeah. So therefore they converge. So they converge along a subsequence, right? So that means that I have UTN, which converges to some U infinity in C2 norm. Okay. Right? Yes? For some,
Yeah.
right? Okay, by Arzela-Ascoli, just Arzela-Ascoli, applied to the second derivatives, right? So therefore they converge in C2 norm to some U infinity, and we've already seen that U infinity has to be harmonic, right? And U infinity restricted to boundary D is equal to F, right? Now this U infinity, this is unique. Why is this unique? This is unique by the maximum principle. right? Because if I have two harmonic functions which have the same boundary values, then their difference is harmonic and it vanishes on the boundary. Therefore, it vanishes identically inside by the maximum principle, right? Is that clear?
Yeah.
Right? Because if I take a function h, which is harmonic and 0 on the boundary, then h is less than or equal to 0 by the maximum principle. And minus h is also harmonic. So minus h is also less than or equal to 0. So therefore, h is also greater than or equal to 0. Therefore, h is identically equal to 0. Fine? Yes? Okay. So a harmonic function which vanishes on the boundary is 0. So therefore, this solution of the Dirichlet problem, this is unique, right? This is unique. And what does that mean? That means that if I take any subsequence, that means all subsequential limits in C2 norm, all subsequential limits of UT in C2D are equal to U infinity. Right? But now if I have a family of functions where all the subsequential limits are equal, right? Then that means the whole family converges, right?
Yes.
So that means limit t tending to infinity, ut exists and equals u infinity. Okay, so that's a sketch of the proof of the convergence of the solution of the heat equation to a harmonic function with the given boundary values. Okay, does this make sense? Right? Is this all right? Yeah.
Yes, sir.
Okay, so essentially I did this because we are going to do the same thing for a nonlinear heat equation. Okay, so what's going to happen is that we will have some sort of nonlinear Laplacian. So what is going to happen? So here we were looking at functions from a domain in Rn, right? So these were going from a domain in Rn into the real line, right? Okay, now what we're going to do is, first of all, replace the target. Okay, so, I mean, see here, they're taking values in a vector space R, right? So that's why you have a linear equation. But the first thing is to replace the target of your maps by some some manifold. Okay, so no longer a linear space. So for example, it could be, the target could be a manifold like this. Okay, a surface of genus 2, for example. Okay. So now your maps, UT will take values in some manifold M. Okay, maybe which is sitting inside some RQ. So N, sorry, N. Okay. Okay. And then, you could look at, well, maps from a domain in Rn into this manifold, right? Which are constrained to take values in N, right? So UT of D is contained in N. Okay, so we impose a constraint on the values of UT. They can only take values inside this inside this manifold. Okay, so that's one nonlinearity in the range side. And then the second nonlinearity you can add is that in the domain, you make the domain a manifold too. So the domain could be some other manifold. Okay. And so now UT will become a map between two manifolds, M to N. Okay. And what happens is, when these manifolds are what are called Riemannian manifolds, so that means you can measure lengths of curves in them. Okay. So for example, if the manifold is sitting inside some RQ, then the tangent vectors to a curve are given by vectors in RQ, and then the length of a curve is just the integral of the length of its norm of its tangent vectors. So you can measure lengths of curves in the, let's say, in the domain and in the range. Okay, then you can define something, a certain nonlinear Laplacian called the tension field of U of a map. Okay, and then you will have a nonlinear heat equation, del UT del T equal to something called tau of UT, where this tau is some nonlinear Laplacian called the tension field. This is called the tension field. Okay. And then the idea is that the main theorem that one shows is that if this this target manifold has what's called non-positive sectional curvature. So non-positive curvature. So we'll define all these terms in the along the way. Okay. So if the target manifold has what's called non-positive curvature, then these maps UT will converge to a map U infinity from M to N, which will be what's called a harmonic map. And that will be a map whose tension field vanishes. So it satisfies some nonlinear Laplacian equal to 0. Okay. So, and this nonlinear Laplacian is related to variations of the first variation of energy of a map. Okay. So harmonic maps will also be critical points of a certain energy functional. Okay, that means if I take a variation of them by a family of maps, then the derivative of the energy along that family will be 0 at time 0. Okay. So all of this that we've done for Rn and the Laplacian, which was a linear setup, this generalizes to maps between Riemannian manifolds in a nonlinear setup. Okay, when the target manifold has non-positive curvature. Okay, so that's why I wanted to do this preliminary discussion of the heat equation, because this will motivate the main theorem of this course. Okay, which is the Eel-Sampson theorem that this harmonic map heat flow, this UT, it converges to a harmonic map as t tends to infinity. Okay, that's the idea. So any questions before we finish?
Can you give a reference for the Schauder estimates?
Aha, yes. Gilbert and Trudinger. Yeah.
Okay.
Yeah, it's a classic book, Gilbert and Trudinger. Yeah. Yeah. So, I mean, what happens is in the general setup of harmonic maps between manifolds, it follows more or less the same scheme of proof that we've done here. You show that the C2 alpha norms of your maps are uniformly bounded, and you show that any limit has to be a harmonic map. And then you get convergence to a harmonic map. So yeah. Okay. It follows roughly the same scheme. That's why I did this sketch of proof, because this is what we will generalize. The main goal of this course is to prove this Eel-Sampson theorem, which gives convergence of the harmonic map heat flow. Okay. That's the goal of this course. Yeah. So I don't know, does this make sense? Is this okay, what we've done so far? Yes? No? Okay. I mean, it helps if you give me some feedback. Otherwise, I just feel like I'm talking to myself. So, you know, it helps to get some.
Yeah, it made sense to me. Yeah.
Okay, good, fine. If someone says it makes sense, that's good for me. Okay, good. Okay, thank you. Thank you. Okay.
Sir, I have another question regarding that course. So, hello.
Yes.
So, I was just looking at the syllabus, and seems like those are at the very end of the course.
Correct.
The things that you do.
But
So,
everything that we do before is building up towards that. Everything that we do is more or less a preparation for the end of the course.
Okay, so and you have also put up a lot of notes on the Google Drive.
Yes.
So, I mean, will you sequentially go through them?
Yes. I will be going through them sequentially. Yes.
Okay, so you haven't started the syllabus?
No.
Okay.
No. This was just an overview of what this course is about, right?
Yeah.
These first two classes was just to give you an idea of what this course is about.
Hmm.
So that's why I did the heat equation as a motivation for what this course is about.
Okay, all right.
So I hope it helped to motivate. If it did, good. If it didn't, well, too bad. I mean.
Okay.
So, yeah. Okay. So, but essentially the arguments that we did here, more or less similar arguments will come up for the harmonic map heat flow. Okay, more or less similar arguments will come up. Yeah.
Like it seems like those things are purely in PD problems.
Yes, but the calculations will become geometric. And what happens is there'll be in the computation, some certain curvature terms will come up. And those curvature terms, if you assume the target manifold has non-positive curvature, then you get control of the solutions. You get the C2 alpha bounds. You can show that the derivatives don't blow up. So that's the point. If the curvature is non-positive, then derivatives of the solutions don't blow up. And therefore you get solutions exist for all time, and then you can further show that they converge. So that's the idea. Yeah.
Okay, I see. So it's just like deriving the analytic properties using the geometry.
Yes. So the geometry becomes important. Yeah.
I see.
Right. Yeah. So before that, we have to do a lot of background material. So that will take most of the course. And then the last part, we'll do the heat flow. We'll talk about the heat flow. Yeah. The harmonic map heat flow. Yeah. That's
So for the existence of the solution, we have just assumed that non-positive curvature on the target space. So
correct.
for uniqueness, we should also need some
Negative curvature. Negative
in the domain.
in the range. Negative curvature.
Oh, achha.
Range. Yeah.
We have to strengthen it to negative curvature. Okay.
Yes.
Okay.
But that is not too hard to see. I mean, what happens is, see, you can apply this to, for example, to curves. If I take, let's say, my domain is S1 and my target is some manifold, right? So if it's, say, of zero curvature, like a torus, what will happen is if I start with some initial curve, okay, the harmonic map heat flow will shorten the length of this curve until it becomes a shortest length curve or a geodesic. Okay. But this is not unique. This solution is not unique because since this curvature is zero, I can slide this. There's a one parameter family of geodesics parallel to this, right?
Yeah.
So I don't have uniqueness of the harmonic map.
Right.
Okay,
we need
but if the curvature is negative, so for example, a negatively curved surface will look something like this. Let me give you. It'll look like a flaring
Right.
trumpet like this. Okay, if I have negative curvature, then if I apply the harmonic map heat flow, there will be a unique in this collar. There will be a unique closed geodesic. There'll be a unique curve of shortest length. So here the harmonic map heat flow will converge to this curve, this unique closed geodesic. So you'll get uniqueness when there's negative curvature. So here the curvature is 0, and here the curvature is negative. Okay, so here you'll get a unique
Solution.
Yeah. So you'll get a unique harmonic map in this case.
Okay. Thank you.
Any more questions? Okay, so yeah, so next time more or less we'll start the actual syllabus of the course. So we'll start from basics and then build up from there. Okay.
And sir, how would you like to divide the entire course structure, like assignment, mid-sem, end-sem?
I haven't thought about that yet.
Oh, okay.
I don't know really. Probably mid-sem and end-sem, just that. Yeah, that
Okay.
should be just a mid-sem and an end-sem. Yeah, that's
Okay.
yeah. Any more questions? Okay, so I'll upload today's notes to the Google Drive folder in that notebook notes folder. I'll do that now. Okay. Okay, so let's stop for today and see you Tuesday.